DINDE is an experimental statistical analysis system written entirely in Lisp. It runs on the Xerox family of personal Lisp workstations and depends on the Lisp object-oriented programming system called loops. In DINDE, we take advantage of this environment and the high-resolution bitmap display to develop a visual representation of a statistical data analysis. In the bottom left corner of the display, there is a window entitled Demographic Analysis. This window is a view of different objects of statistical interest, and the view itself is called an analysis map. The objects in this view are three: a string vector containing the names of 49 different countries, a float vector containing the number of infant deaths per 1,000 live births for each of the 49 countries, and another float vector containing the per capita gross national product for each of the 49 countries. These are independent objects in DINDE, and as such may be interacted with through the analysis map using the mouse. In particular, we can give each of them a name, or we can add notes to them as we learn more about each object. Pervasive throughout DINDE is the ability to zoom in on the details of every statistical object. Zooming in on the country string vector, for example, produces a number of windows which display the internal details of that string vector. As we can see, its elements are the names of each country, and they are arranged in alphabetical order. To remove this detail from our display, we need only close the window. Similarly, this window, the analysis map itself, is a view on these three statistical objects. As such, it has behaviors which allow us to narrow the view, perhaps removing some of the objects that are already in the display, or widen the view, adding new objects to the display. Most often in DINDE, we add a new object by selecting the Add a New Kind of Analysis node. Selecting this, we're prompted for the name of the class of that node. All such classes are contained in a window called the DINDE Toolbox. Opening the Toolbox, we see all of the possible classes that are available in DINDE. These are arranged in order of increasing specialization from left to right. In particular, then, we have a general kind of array and three special cases for that array, namely matrix, scalar, and vector. Then in turn, for each of these, we have either matrices with Boolean elements, float elements, or string elements, and so on. We also have a whole host of graphics available in DINDE. These are divided into one-dimensional plots and two-dimensional or XY plots. Again, you see that the one-dimensional plots are either box plots or histograms, and two-dimensional plots are QQ plots and scatter plots and dynamic scatter plots. And these are again further specialized. A different kind of class is something we call a statistical situation. These represent less familiar artifacts of a data analysis, such as fits, or decision nodes in the analysis, such as a bivariate regression. For this particular data set, I'm interested in regressing the infant death on the per capita GNP, so I select a bivariate regression from the toolbox, and I'll close the toolbox. DINDE constructs the bivariate regression and then prompts us in this black prompt window for the values that a bivariate regression needs. In particular, it needs an X variable, an explanatory variable, which I'll select to be the per capita GNP, and a Y variable, which I've decided will be infant death. I'm also given the option of attaching labels to each of the points in the bivariate regression, and I'll select the country. Back in the analysis map, I'm now given the opportunity to link this new node in the analysis to existing nodes in the display. To demonstrate the logical flow of the analysis from the two data vectors to the bivariate regression, I'll choose to link the bivariate regression to each of them. In this way, we see that the flow of the logic is from the two data vectors to the bivariate regression. In DINDE, we represent a statistical data analysis as a collection of directed acyclic networks, where the nodes of each network represent artifacts of the analysis or decision points of the analysis, places where we may entertain taking new actions. As such, I have the ability to rearrange the nodes of the network in a way that makes the most sense to me for the logic of the analysis. Thus, the analyst is given the power to actually break links and make links between objects in the network. The analyst is also allowed to insert objects called memos between two nodes. These objects will just be repositories of information on the logical flow of the analysis. They'll just have notes added to them. Another way in which the analysis can grow is by examining each individual node and seeing what specific actions can be taken from that decision point. Here for the bivariate regression, we see that we can inspect the data in a variety of ways: scatter plots, histograms, or box plots. We can fit a straight line to the data, either using the resistant line fitting technique or the least squares fit. If we're not certain what to do at this point, there are also some suggestions made available. When selected, the suggestions produce canned text which describe, given the context that we're interested in doing a simple bivariate regression, what one might do first. In this case, it says that generally one should inspect the data visually. In particular, look at a scatter plot. Let's return to the analysis map then and do exactly that. So selecting the methods available for a bivariate regression, we look at the inspect data and choose scatter plot. Selecting scatter plot causes DINDE to produce a new object called a dynamic scatter plot and to prompt us for a position on the display to show the plot. Here we see the infant deaths versus the per capita GNP for each of the 49 countries. We can identify countries simply by pointing and selecting them with the mouse. This inverts the displayed cross and shows the label associated with that point in the display. If we like, we could label the point on the display itself. Just like bivariate regression, scatter plots have specific methods associated with them. In particular, we could add a straight line of some sort, or smooth the y's, or save the displayed data, or look at some suggestions if we're not certain what to do. Because of the curvilinear relationship present in the plot, I'm going to look at a smooth of this plot. In particular, I'm going to look at a running linear smooth of the y's. Then calculates the smooth and adds it to the plot. As was the case with the individual points, the smooth can be selected and it displays the information that it's a 10% span, and it can be labeled. An alternative to fitting a smooth curve to this data, we could try and straighten the plot itself by choosing a re-expression on the plot menu.